This video is purely conceptual. We're not going to be looking at math or solving problems. And we're going to go over two concepts, damping and resonance. So first, damping. Why does a spring not bounce forever? Because as it bounces up and down, energy leaks out. And that fading motion is called damping. So if you graphed it, it'll look something like this. Slowly die out and come to a stop. Real world motion always has resistance that converts some of your kinetic energy into stuff that doesn't help it move. So eventually it'll stop. There's resistance like air drag, friction, and this resistance pulls the energy out and decreases your amplitude over time. There's three types of damping. The first type is called underdamped. When something is underdamped, it means the oscillation continues until it fades out, like a spring slowly coming to a stop or a pendulum slowly coming to a rest. The second type of damping is critical damping. So when something's critically damped, it means it returns to equilibrium as fast as possible. It's ideal for car shocks, automatic doors. So it doesn't overshoot, it just fast resets. It will look something like this. So your normal bouncing spring looks like that. Critically damped systems will bounce up once and then will snap back to equilibrium as fast as possible. There's no overshoot until it returns to equilibrium. It's just that. The last type of damping is called overdamping. This means that it returns to the center slowly with no oscillation. There's too much resistance which makes it sluggish. So look at this. Underdamping means it slowly fades out. It does overshoot over and over again until it returns to equilibrium. Overdamping will look something like this. It'll do its initial bounce up. It'll slowly return to the center. It's sluggish. So damping actually doesn't affect frequency. It affects amplitude, the maximum height. A car's suspension is critically damped, which gives you a smooth ride. There's no bouncing up and down. A phone and its vibration motor, so when someone calls you and the phone's vibrating, it's controlled underdamping. It looks like that until it stops. How about the second thing that we're going to cover in this video, resonance? Why do bridges collapse if wind hits at just the right frequency? This has actually happened in real life. So let's compare damping and resonance. Damping is when motion fades as energy is lost. Resonance is when motion is amplified, when energy is added at the perfect rhythm. Core idea is that every oscillator, so anything that vibrates, has a natural frequency rhythm that it likes to bounce at. If you force it with small pushes at that exact frequency, and each push lands perfectly, it stacks up and it amplifies it. So a small force plus the right timing equals a gigantic explosive response. What happens is that the amplitude builds dramatically, and with no damping, it grows without limit. So you need the damping to keep it in control. In real life, there's good and bad resonance. A good application of resonance is radio antennas and musical instruments. A dangerous application of resonance is bridges collapsing. You can search up this specific bridge, TACOMA. The wind frequency hit just perfectly and the bridge collapsed. Here's another dangerous thing that resonance can do. Machines can vibrate out of control. And earthquakes plus skyscrapers, it's a bad combination. This makes studying 10 times easier. Go download the free cheat sheet in the description and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.